Now let's look at a more challenging problem. Here we will incorporate friction as well, but the main setup difference between this problem and the other problems that we have looked at is that now the book that we considered in the previous problem is placed on an inclined surface, so not on horizontal surface anymore. So let's read the question. We have the book placed on an inclined surface as shown, and the surface is rough. What does this mean? Rough refers to the fact that the surface has friction, and if this were replaced by smooth, then we would be able to ignore friction. What is the normal force and friction on the book on this inclined surface? Given that the static coefficient of friction is equal to static coefficient or kinetic coefficient of friction is equal to 0.3, and see that there is no unit attached to this coefficient because it is just a constant coefficient, no units, it is just a number. And mass of the book is still 1.2 kilograms as we considered before. The angle of the incline is 15 degrees, and we would want to find the normal force and the friction on the book. First of all, let's think about how this is going to move. Intuitively, you can just say that, well, the inclination of this plane means that the book will want to slide downwards, right, because of gravity. And you would be correct, because the general inclination of this book should be along the plane downwards, right? So how do we approach this problem? First and foremost, we have to draw the free body diagram. Let's go ahead and do that. Free body diagram, remember, only has the body in question. First force that we always write down is the weight, mg, for the book or any object. And remember that gravity always pulls you vertically downwards, always pulls massive objects vertically downwards, regardless of the incline of the plane or surface that the object has been placed on. Okay. Then we also know that this surface will exert a normal force on this book because they're in contact, and the normal force must be perpendicular to the surface in question. Now the surface is this inclined surface, so the normal force must be perpendicular to the incline. So the normal force would now look like this. What are the other forces acting on this book? Well, if it's trying to slide down, right, then before it slides, we have static friction acting on it. After it begins to slide, we will have kinetic friction acting on it. And why is the frictional force directed up along the plane? Because the intuition tells us that the book will slide down along the plane. Friction will oppose this sliding, and hence will try and resist by exerting a force up along the plane. That is our free body force diagram. Before we move on and write down Newton's second law equations, let us first think about how to approach this problem on an inclined surface, because we have not done those kind of problems before. So there is some geometry of this inclined plane that we need to be aware of. I'm going to be discussing a very general idea of any object on an incline. Okay. So say this is an inclined surface, inclined at an angle theta with the horizontal, and you have a particle or an object here, correct? And what are the forces on it? So we must have the weight of the particle directly downwards, and we must have the normal force perpendicular to the inclined surface. And let's say that the inclination of this particle, because there are no other forces acting to prevent this inclination or tendency of the particle to move down along the slope or down along the plane. So we'll also have friction force. That friction can be static or kinetic based on if this particle has started sliding or just before sliding. Okay, just before sliding it will have static friction, just after sliding it will then have kinetic friction. All right, now if you have noticed in our free body diagram, we haven't defined an axis. Why? Because we haven't seen this kind of problem yet. Now our next job would be to define an axis. The general rule of thumb is the axis should be chosen such that one of the axis direction is along the acceleration of the object being considered on the inclined surface. As we have said, the tendency of the object is to move down along the slope. So we would want the axis, one of the axes, to be parallel or anti-parallel to our acceleration. Okay, so you can choose this direction to be positive or that direction to be positive, it doesn't matter. So I'm choosing this direction to be positive x, and because remember we can choose coordinate axis arbitrarily. However, there is a certain rule that we must follow. You can choose one axis arbitrarily, but the other axis is determined by the first chosen one. So if you chose your plus x like in this weird manner, then your plus y must be perpendicular to this weird plus x. So you cannot draw plus y like this. This is not right because that angle is not 90 degrees. It's not perpendicular to your plus x. So the only restriction about choosing axis is then you choose one axis along the direction of acceleration, which makes the problem a lot easier, as we will find out. We call this plus x, and to that we add the perpendicular y-axis. All right, so I'm choosing upwards to be positive y and up along the plane to be positive x. All right, so plus y is actually perpendicular to the plane and plus x is actually parallel to the plane. All right, our next job is to break down forces that are not along our chosen axis into their components. Right, let's see which of these are not along our chosen axis. Friction is up along the slope, so it is actually parallel to plus x, so we don't need to break friction down into its components. It is already along the positive x-axis, so it has only one component, the x component. Normal force is parallel to plus y and perpendicular to friction, so normal force is also along an axis, the plus y axis, so we don't need to break down normal force into its components because it only has one, the y component. However, mg, the weight of the particle, is not oriented either parallel or perpendicular to the x-axis or y-axis. It is not oriented with the chosen coordinate system. So what we need to do is we need to break mg down into its components. So remember, components must be along our chosen coordinate system. So let's enlarge this and see what this looks like. This is plus x plus y. The particle is lying somewhere here, which is on the slope, and the slope can be considered to be the x-axis because they're parallel. The weight acts vertically downwards regardless of the chosen coordinate system. Then we can see that this weight falls under the negative x direction and the negative y direction, this region right here. This region, we see that as you move more and more in this direction, then x becomes more and more negative, and as you move along this direction more and more, y becomes negative. All right, so both of these components, how would they look like? They would look like one component will go in this direction, the other component will go in this direction, right? So we will call this wx, because remember this is equal to w, and we will call this wy. Note that these components are now not horizontal or vertical components. They are now x and y components with respect to our chosen coordinate system. So translating it into our own diagram gives me these two components. We call this wy, we call this wx. Now our next goal is to find what these wx and wy is. So we have formed the right angle triangle that we usually do to find components of vectors. However, we are missing the angle that we use so that we are unable to use trigonometric relations to get to these components or to find these components which will enable us to solve the problem. So we have to find what that angle is. Now remember, we are given the angle theta, the angle of the inclined plane. So we will try and use this angle theta and get to somewhere that will give us some angle of this newly formed triangle that we need to find our components. So if this is theta, then this triangle with the original weight, this triangle is 90, is a right angle triangle. Now if this is 90 and this is theta, we know that sum of all angles of a triangle is 180 degrees. If this is 90, this is theta, then this is nothing but 180 minus 90 minus theta, which means this is 90 degrees minus whatever theta may be, right? Then see that if this is the newly formed triangle and this is 90 degrees, then note that this angle that the plane forms with the y component must be 90 degrees. Why? Because x and y axis are perpendicular to each other, right? So if this whole angle is 90 degrees and this is 90 minus theta, this angle is equal to theta, because if this full angle is 90 and this is 90 minus theta, we have 90 minus theta equals to this angle, which gives me theta. All right, this is how you determine the angle which you will use in the triangle with your components. All right, so this is a very general rule. You can incorporate this into any problem with inclined surfaces. Now what if the incline was arranged differently? All right, this is something you would find in your lecture notes. All right, I just wanted to shift it around but show you both kinds of orientations. We'll start with our free body diagram with the force of gravity, that is the weight, going straight down, and we will have the normal force which will always be perpendicular to the surfaces in contact. So it will always be perpendicular like that. Okay, there's a surface, that's the normal force perpendicular to it, and then this particle or object will have the tendency to slide in this direction, right? Then if this has friction, if this inclined plane is rough, then the friction would be to oppose the sliding motion, so it will be directed up along the plane. All right, now these are the forces that are on my particle. How would we then go about finding the components? Well, we have to determine the axis first. In this problem, I'm choosing the axis to be in the direction of the acceleration, the x-axis, and the y-axis is just perpendicular to the x-axis, positive in that direction. All right, So x-axis is again parallel to the plane, while the y-axis is just perpendicular to the plane. So if we look at the forces, we see that normal force is parallel to the y-axis. So normal force again has just one component, the y component. So we don't need to break it down into its components. The friction is anti-parallel to the positive x-axis because it is directed in the negative x-axis. But again, it is only a x force. There is no other component to it. So we don't need to break it down. The only force again that we have to break down is our weight, because it is not oriented with our chosen axis. So let us find our components. The components, if I enlarge this axis, you have plus x going this way, you have plus y going that way. The weight of the particle here is straight down. Then you can see that as you go in this direction, x increases in a positive manner, right? And as you go in this direction, y is actually increasing in a negative manner. So the components would look like these. So this we call wx, this we call wy. All right, and like always, the intersection of the two components would be 90 degrees. Okay, so on this diagram, it would look like this. We have the y component along the negative y-axis, and we have the x component along the positive x-axis, forming a right angle. All right, then our goal would be to find an angle for this triangle, which will allow us to use trigonometric relations, right? How do we do that? Well, again, we use geometry. If this is theta, this is 90 degrees, right? We can just look at this and say that this is a straight line cutting through the horizontal. So this must mean it is 90 degrees. And if this is 90 and this is theta, this must be again 90 minus theta. If this is 90 minus theta, we know that this is also a straight line which is perpendicular to this incline. So this whole angle is 90 degrees. So this angle must be theta, right? Just like before. Now, what is our wx and wy? This is our triangle that we are working with. Let's call this the overall resultant w. And this is 90 degrees. This is wx, this is wy. And this is the angle, all right? So this is our adjacent, because both of the angles 90 degrees and theta are on this side, and this is our opposite. It is opposite to the angle theta. Wx is opposite, wy is adjacent, and w, the overall weight, which is equal to mg, is the resultant vector. Then our components become, the x component can be found by using w and wx, which is opposite over hypotenuse. So then wx over w equals sine theta. Therefore wx is w times sine theta. Okay, similarly wy is then w cosine theta, and remember w is nothing but mg, so mg times sine theta, mg times cosine theta. Okay, so now let's look at a problem with a different setup. We have set the book up not on a horizontal desk anymore, but on an inclined surface. The angle of incline of the surface is 15 degrees, and we say that the plane is rough. This statement that something is rough means that we are considering friction. If something is considered to be smooth, then we don't have to think about friction. For the rough surface, the coefficient of friction, whether it be static or kinetic, is 0.3. And notice that this is just a number with no units because it is a constant coefficient. It is based on whatever surface is being used. So if the surface has more friction, the coefficient will be more, and less friction, the coefficient will be less. And the mass is still the mass of the book from before, which is 1.2 kilograms. We want to investigate that at this incline angle and all of these properties of this plane, that the plane is rough with this kind of coefficient of friction, does the book indeed start sliding downwards? And if it, because the initial tendency would be to slide downwards, if it does, it will automatically slide downwards. It won't slide upwards because of gravity. So we want to investigate whether it does it slide downwards, and if so, then what is the acceleration? All right. The first thing again we do is always draw the free body diagram. Let's start with that. Now we will use the concepts that we learned of how to set up all the forces on an incline. So remembering that we need to set one axis that is in the direction of the acceleration, and the other axis should be perpendicular to that to the first axis. We will choose here the axis like this as plus x going down along the plane, and plus y is perpendicular to the plane and perpendicular to the x-axis chosen. All right, what are the forces on this block? As always, the first force that you should think of is the weight, because it is always there. If you have mass and gravity, this is the weight. The normal force is perpendicular to the surfaces touching. So this is the surface, these are the surfaces touching. So the normal force will be perpendicular to it. So perpendicular to the surface, it looks perpendicular, I guess, will do. Normal force, and then since the tendency of the book is to slide downwards, the friction will be upwards, okay, up along the plane. So this friction, we don't know is it static or kinetic at this point, because we don't yet know if the box does start sliding. All right, so let's call it F for now, and we will change the notation as before. Let's call it Fs for now, actually, because if it's not moving, it's static. If it's moving, we will just say that it is kinetic friction. All right, this is our free body diagram. Now our second thing to do would be to set up Newton's laws, Newton's second law equations. However, we don't know all the forces along our chosen axis. More specifically, N is along the y-axis, so it is a y. It only has y components. Fs is along the negative x-axis, so it only has an x component. W is not along either axis, and hence it must have two components with respect to x and y axis. So let's find out the components of this. To do that, we need to know that the angle of incline is 15 degrees, and as we have worked out before, the components will look like one going straight down perpendicular to the plane, and one going parallel to the plane. This is Wy, this is Wx, and the magnitude, this resultant, is W, the weight. And remember what W is? W is equal to the mass of the book times the acceleration due to gravity, mg. Before we set up Newton's second law equations, let us first write down the components of W. If this is 15, we have learned how to manipulate this angle and write down angles in a triangle. If this is 15, this is also 15, as we have just seen. Then makes our lives easier, since we know that this is a right angle. The angle between the two components must be a right angle. So WY is W times cosine of 15 degrees, and W is mg sine 15, and WX is W sine 15, which is just mg sine 15. So these are the two components of weight that we need in order to write down Newton's second law equations. So now let's write down Newton's second law equations. In the x direction, we have the equation summation of the forces in the x direction is equal to mass times acceleration in the x direction. What are the forces in the x direction? Remembering that x and y axis is tilted like so. Summation of fx is equal to, we have, what are the forces? We have fs going in the negative x direction up along the plane, and wx going down along the plane. Okay, so we have a positive wx, a negative friction, that is equal to m times ax. Let's call ax as a is the acceleration down the plane if there is any. Okay, so we don't know if it's 0 or non-zero, so we keep it as a. And wx we found out is mg sine 15 minus fs is equal to ma. Let's call this equation 1. Now let's write down the equation for the y components of forces. Fy equals may. What are the forces in the y direction? We have the normal force and we have the y component of the weight. Normal force is in the positive y direction, so plus n. Wy is in the negative, so minus wy. Wy we just found out as mg cosine 15. Mg cosine 15 equals to, remember that the box or the book is not sliding in the y direction, it is only sliding along the plane. So acceleration in the y direction is 0, so this side is 0. Alright, so then n is equal to mg cosine 15. The normal force is equal to the y component of the weight. Since the two y forces are equal to each other, that means there is no motion in the y direction. In other words, there is no resultant force in the y direction to make something accelerate in that direction. That is the concept of Newton's second law. Let's call this equation 2. Now it's time to check if Wx is actually overcoming the friction to cause an acceleration down along the plane, right? So, but what is friction? We know friction, the static friction, is less than equal to mu s times n, the static coefficient times the normal force. We have found the normal force, which means that the static friction is less than equals, mu is given to us as 0.3 times the normal force is mg cosine 15, m is 1.2, g is 9.8 times cosine 15. What does this come out to be? This comes out to be 3.41 newtons. So the frictional force, the static friction of this surface that this book feels if it tries to slide downwards is 3.41 newtons. All right. Now our job is to check if this static friction, this limit, that this just means that the static friction is always less than or equals to 3.41. So static friction cannot be more than 3.41 newtons for this specific surface on this book. All right. And then we consider equation 1. What do we have in equation 1? Left hand side. In the left hand side we have mg sine 15 minus fs. There will only be an acceleration if this force, that is the x component of the weight, exceeds friction in that the book starts sliding down along the plane. Why? Because this x component of the force is the one responsible to cause any sliding motion down along the plane. All right. So to cause sliding motion, Wx must be more than the limiting frictional value, which is 3.41 newtons for this problem. Let's see if it is so. Is mg sine 15 minus fs greater than 0? Let's check. What is mg? 1.2 times 9.8 times sine 15. And what is fs? Well, fs is 3.41 as we have just calculated. So let's see, what is this? This is 3.04. 3.04 is smaller than 3.41. So it is not greater than 0. In fact, it is less than 0. So the difference between the x component of the weight and the friction is less than 0, meaning the friction is more than, the static friction is more than the x component of the weight, which is responsible for any tendency to slide down the slope. Hence, this must mean there is no acceleration. We don't even have to go ahead and calculate this equation, because with no other forces present, the x component of the weight is not large enough to cause any sliding down along the plane. All right. This is how we can think of static friction.